It is well known that in finite element analysis, the entire structure is divided into smaller elements. These smaller elements are called as elements, and these elements will be connected by means of a characteristic nodal points called nodes. The unknowns are available in the nodal points, and we have discussed that available in the nodal points in the previous slides. The choice of the coordinate system is based on the type of analysis and based on the type of the structure that we use. If we employ a rectangular coordinate system which is aligned with the global coordinate system, it will be easy to identify the solution. But whereas if we use a triangular element, a definite coordinate system must be used to get and identify the solution of the unknown. So in finite element method, there are three coordinate systems that are referred, such as global coordinate system, local coordinate system, natural coordinate system. These are the generalized coordinates for defining a polynomial form of interpolation function. Global coordinate system is defined as to define the entire points in the entire structure is called global coordinates. For example, when we take a truss structure, when we define the entire points of the structure that represent the entire structure, that is referred to as global coordinate system, and the truss member falls in x and y direction similar to the global coordinates or global axis. When a typical coordinate system followed for an individual element of the structure, it is then called as local coordinate system. But in finite element analysis, the final equations are to be found in a common coordinate system called global coordinate system. So as discussed earlier, the coordinate system that is followed for that particular element is called as local coordinate system. But finally, all this element which are inclined with some angle which has its own coordinate system is called as local coordinate will be combined to form and follow the global coordinate system. So if the member is inclined and this inclined member with the nodes 1 and 2, the axis is taken as x dash, and similarly the vertical axis is taken as y dash. If the member is inclined in the third quadrant or the fourth quadrant of the axis, again the horizontal axis is taken as y and the vertical is taken as x. So the axis corresponding to that particular element is called as local axis, and the coordinate system followed is called as local coordinates. So the natural coordinate system is a system of coordinates that permits the specifications of the point within the element by a set of dimensionless numbers whose magnitude never exceeds unity. It is used to assemble element properties such as stiffness matrices. Here the natural coordinates are nothing but the weightage given to the nodal coordinates. The total weightage at any point is unity. So L1 plus L2 will be equal to 1. So this is the image that shows the natural coordinate system in 2 dimensions for a triangular element. Similarly, for the natural coordinate system for a rectangular element, so this is the natural coordinate system. The natural coordinate system in 3 dimensions. So this is a tetrahedron that has the natural coordinates in 3 dimensions. Similarly, the natural coordinates for hexahedron. Shape function is one of the important terms that one will come across in finite element analysis. For example, when we want to calculate the area of an irregular boundary, consider dividing the total area by as many number of squares, because it is easy to anyone to calculate the area of the square. But whereas wherever we have a curved edges in that particular boundary, we can assume that particular line to be interpolated with certain functions. So this method of assuming some function over a regular or irregular shape is called shape function. In other words, in order to find the variables at the nodal points of the element shape, the shape function is introduced. The function that relates the field variable at any points within the element to the field variable of the nodal point is called a shape function. So let me repeat it once again. The function which relates the field variables at any point within the elements to the field variable of the nodal points is called as shape function. For instance, let us take a 3-noded triangular element with the 3 nodes inside the triangle. The values of the displacements are computed only at the nodes, but whereas in case of these 3 nodes which are inside the triangle, the values of the displacement must be obtained. So in case of this particular triangular element, shape function must be used because it is easy to calculate the displacements or the unknowns of the nodes that connects the elements, whereas the nodes that are not in the elements but representing the structure can be calculated by using the shape functions. And this shape function is also called as interpolation and approximation function. In the 2-dimensional stress analysis, the basic field variable is displacement. So the displacement u is the summation of ni into ui and v is the summation of ni into vi, where n is the shape function. For a 3-noded triangular element, the displacement p of x comma y is given as u is equal to summation of ni ui is equal to n1 u plus n2 u2 plus n3 v3 u3. Similarly, Similarly, for u, the displacement along v direction or the displacement along y axis is given as v is equal to summation of ni into vi, which is equal to n1 v1 plus n2 v2 plus n3 v3. So when we write in the terms of matrix, u v is equal to n1 0, n2 0, n3 0, 0 n1, 0 n2, 0 n3, u1 v1, u2 v2, u3 v3. So u1 v1 are the displacement in x and y, and n1 to n3 are the shape function in x and y axis or x and y direction. So the above expression can be written like this: delta, which is nothing but a displacement, is equal to shape function into the displacement of that particular element. The total displacement of the structure will be equal to the shape function into displacement of that particular element, where delta E is the displacement at any point in the element and n is the shape function and delta is the vector of nodal displacements. Similarly, in case of a 6-noded triangle, delta 2 cross 1 is equal to shape function 2 cross 12 into the displacement for that particular element 12 cross 1. In case of 4-noded rectangular element, the shape function is represented here. Delta, the displacement for the 4-noded rectangular element, is equal to shape function, which is 2 cross 8 into delta E, the displacement for that particular element. Since shape function is an interpolation or an approximation function that is assumed to find the displacement, now let us see the different polynomial shape functions that are widely used in finite element analysis. Since these polynomial equations are easy to differentiate, these polynomials are generally used as a shape function. It is easy to calculate mathematically, and also differentiation and integrations of this polynomial is very easy. And using polynomial, any function can be approximated. So the polynomial shape function for a constant, for a linear function, and for a quadratic function is shown in these images. Now let us see the one-dimensional polynomial shape function. So let us take the general one-dimensional polynomial shape function of nth order as u of x is equal to alpha 1 plus alpha 2x plus alpha 3x square plus up to alpha n plus 1 into x to the power of 1. So the one-dimensional polynomial shape function in the matrix form can be represented as u is equal to matrix u into alpha, where the one-dimensional polynomial shape function in the matrix form is given as u is equal to g into alpha, where g is equal to 1 x square up to x to the power of n, and alpha t is alpha 1, alpha 2, alpha 3 up to alpha n plus 1. So thus in one-dimensional nth order complete polynomial functions are m is equal to n plus 1 terms. Similar to one-dimensional polynomial shape function, let us see two-dimensional polynomial shape function. The general form of two-dimensional polynomial model is u of x comma y is given as alpha 1 plus alpha 2x up to alpha m y to the power of n, and in v, the displacement in v is alpha m plus 1 plus alpha m plus 2 up to alpha 2m y to the power of n. So the two-dimensional polynomial shape function delta is given as g into alpha, which is g1 0 0 g1 into alpha, where g takes the value of 1 x y, x square x y, product of x y, y square x cube up to y to the power of n, and alpha transpose is alpha 1 to alpha 2m. So it may be observed that in two-dimensional problems, the total terms of m in a complete nth degree polynomial is m is equal to n plus 1 plus n plus n plus 1 into n plus 2 divided by 2. The first three terms are alpha 1 plus alpha 2x plus alpha 3 into y. Similarly, for n is equal to 2, m is equal to 2 plus 1 into 2 plus 2 by 2, which is equal to 6. Since we know that the first 6 terms are alpha 1 plus alpha 2x up to alpha 6 y square, and another easy way that is available to remember the complete two-dimensional polynomial is in the form of Pascal. For a constant function it is 1, for a linear function it starts with the x and y. Now let us see three-dimensional polynomial shape function. Let us consider the general three-dimensional shape function for nth order complete polynomial. The nth order complete polynomial is given as u, v, w, and the corresponding equations are displayed here. The three-dimensional shape functions in terms of alpha and g is given here, where the value of g takes from 1 x y z x square up to z x n to the power n minus 1. The three-dimensional polynomial shape function alpha transpose is given as alpha 1, alpha 2, alpha 3 up to alpha 3m. Nth order polynomial in three-dimensional case is having the number of terms m given by the expression m is equal to n plus 1 into n plus 2 into n plus 3 divided by 6. Based on the value of m, the number of terms m will vary. For the value of n is equal to 1, m takes the value of 4. For the value of n is equal to 2, m takes the value of 10. Thus, the second degree complete polynomial is given as like this. So in finite element analysis, when we use a shape function, we need to look for the convergence requirements for the shape functions. The convergence requirement for the shape function is nothing but the degree of level of accuracy closer to the actual solution for the assumed shape function. As the shape function, interpolation function or an approximate function is used to calculate the unknown displacement in finite element method, the value of the displacement found from the finite element method will be lesser than the exact values. So the convergence of FEM solution is based on this, the percentage of error on the y-axis and the exact solution. So the selection of the shape function should be closer to the exact solution in order to decrease the percentage of error with the exact solution and the obtained solution.